Okay, we're going to do a little parametric equations with the calculus here. So first thing is I gave a little derivation over here of why we have our formula here. It comes from this basically. You're finding this, you have this curve out here, and you have the couple points. This is your delta y, and this is your delta x. And these ordered pairs, this one here is, we'll say this first one down here, this point ordered pair is, let's see, f of t, g of t, and this ordered pair up here is f of t plus delta t. And comma g of t plus delta t. Okay, so your x and y coordinates based on the definitions of those functions in here. Okay, so there's that x is switching, moving, and so is that y. Okay, so when we find dy dx, then we're going to have to take the limit as delta x approaches 0, delta y divided by delta x. Well, if delta x is approaching 0, then so is delta t. So we can write this. And delta y from the diagram you can see is just the change in the y coordinates here. So I have that, and delta x is the change in the x coordinates. So you have this minus the f of t. Now, if you divide both numerator and denominator by delta t, and you can do that because it's not 0, it's heading to 0, but it isn't 0, you'll get these two expressions, and we recognize in this form, both of these are just derivatives. The numerator is g prime, the denominator is f prime. So another way to write that is just dy dt over dx dt. So that's what we have, dy dt over dx dt. Let's look at an example. Go right into this one. Okay, I'll leave that there. Oops, I won't be able to see that. Right there. Okay, so we want dy dx first of all. So dy dx, it's going to be dy dt over dx dt, which is a 3 over 1/2 root t like that, which is a 6 root t. Now evaluated at t equal 1, this becomes a 6. Okay, second derivative, we want this. And as you can see from the definition of the first derivative, we really just need to find the derivative of y with respect to t and then divide it by dx dt. So that's a derivative. So if we're finding the derivative of a derivative, then we want to find the derivative of the y, which in this case is a derivative itself, dy dx. So we're finding d dt of now it makes more sense if you see it written like this. So we're taking this, finding its derivative with respect to t, and then dividing it by dx dt. That's what its differentiation is. Just so happens that this function that we're taking derivative of is itself a derivative. Okay, and then that'll give us our answer. So we come in here, we're going to need to first of all find the derivative of dy dx with respect to t. Now here is the function. So you want its derivative, which would be 6 over 2 with a root t like that. And the denominator will be just another dx dt, which was a 1/2 over root 2 like that. Now this reduces to just a 6, which is constant, therefore the derivative at 1 is also a 6. Okay, now I just want to say that for some functions, I mean, if just to keep perspective there, what you're finding is if we convert it to rectangular form, what would we find? Well, let's say x squared equals root t, equals t. Okay, and we know t has to be positive, so we didn't lose anything there. That means y equals 3t squared minus 1, and 3x squared. And we now have the rectangular form for this parametric set here. So dy dx would just be a 6x. Now, notice since x is root t, that's exactly what we have here, 6 root t. Second derivative, and by the way, at t equals 1, x equals 1, so we'd have the same derivative. And this is, now second derivative would be a 6, which matches this one. So what we did is consistent. Everything's good. Let's do the next one here. Okay, we want dy dx. Let's do y dt over dx dt, which is, let's see, dy dt would be a 2 secant squared. Dx dt would be a secant t tangent t, which then reduces to 2 secant t times a cosine of t over sine t. Well, that's just 2 cosecant t. Now, okay, evaluate that. Dy dx at pi over 6 is 2 over the sine of pi over 6, which is 2 over a half. That's a 4. Okay. Now, let's find the second derivative. This will be, we're finding the derivative of this, of the first derivative. The derivative of the first derivative will be minus 2 cosecant t cotangent t divided by dx dt. Well, that's the same as it was before. Dx dt was the secant t tangent t. Okay, so we'll show a little bit of the work here. Let's write that says minus 2.
Hey, stop looking around.
Okay, we're back. I had a little press the wrong button there and boom, got some craziness. Okay, we're back. Okay, let's see. We got 2 secant square. Where were we? Simplifying. Okay, so this would be, oh, here, cosecant. So we have minus 2 sine of t, and the cotangent is a cosine of t over sine of t. The secant would be a cosine up here. Tangent would be cosine over sine. So all that gives minus 2 cosine cubed over sine cubed. And this is minus 2 cotangent cubed. Okay, evaluated at pi over 6. We'll say pi over 6 is a minus 2. Let's see, cotangent cube pi over 6, like that. Down here, minus 2. Let's see, the cotangent pi over 6 will be, let's see, cotangent be 1 over 3 root 3 over 1. So we made a root 3 cubed, which is a minus 6 root 3. Bringing out that 3. Keeping 3, bring 1 out. Okay, so there's your answer for that. All right. Okay, back here. Let's see. Okay, here's our formula. And we're going to use this one. This is easily gotten from this form here. Assuming we'll assume that this is a form that we're taking, we're integrating with respect to x here. Same can be done with the other derivative if you wanted to. But using just substituting in our value for the derivative in parametric form here, you will get to this with a little bit of algebra. Okay, so that's all it takes. Notice it says make sure not to integrate over the interval more than once. So we'll have to keep track of these points A and B, which correspond to t values, and make sure we don't skip over that. Okay, let's go ahead to an example here. S will be equal to t is from 1 to 5, and we want the square root of, okay, we need some derivatives here. dx dt is 1 over t, dy dt is 4. So we have 1 over t squared plus a 6t dt. Okay, now I wonder if we can integrate this, or if it just says set up the integral. Doesn't say to do it, so let's see what we have here. This would be 1 plus 16t squared over a t dt. Okay, so that's not something that we can actually integrate readily. So that would be either a problem for substitution, like a trig substitution, or a table, if you had a table, or a calculator. Okay, so we'll just leave it like that for now. Let's go to this other one. Now this one says set up and evaluate. This just said set up, so we weren't really forced to calculate. Let's set this up and evaluate. So let's get the derivatives first. Now notice I keep writing dx dt. When it comes to these parametric forms, many times it's simpler just to write an x with a dot over it. And that is universally accepted as the derivative of x with respect to t. First derivative. If you were talking about a second derivative, then you'd have x double dot. It's just so much easier. So we can use that notation if we want. So let's go ahead and here. Let's see, we have a minus e to the negative t cosine t, and then minus e to the negative t sine t, which we can write as minus e to the minus t times a cosine plus a sine. Okay, y dot minus e to the minus t sine t plus e to the minus t cosine t, which is an e to the minus t times cosine t minus sine t. All right, now let's start filling in our integral here. We're going to go from 0 to a half, and we want our derivative squared now. So dx dt squared, which is going to be e to the minus 2t, and we'll have a cosine of t plus a sine t, and the squared, and then plus the square this other derivative, dy dt, square that, we have e to the minus 2t cosine t minus sine t squared dt. Okay, so there's a little bit of algebra here, and hopefully it pays off when we get it all done. You're gonna make a lot of room in here. E to the minus 2t, we're gonna factor that out. And we're gonna expand these. So this will be cosine squared plus 2 cosine t sine t squared plus another cosine squared t minus 2 cosine t sine t plus a sine squared t. And then that gives 0 to a half. Let's see, now this, I should have pulled this out right away. That's just e to the minus t. So I square it. Okay, so you pull that out. And now inside here, let's see, what do we have? Well, I got 2 of these added together makes just 2 because each one of them is a 1. This plus this is 1, and this plus this is a 1. So that makes 2. These two things cancel. They're gone. So I guess I can shrink that. That radical. We don't need something that big. It's just root 2, like that. Okay, so not a bad integral. You can put out that root 2. You'll have a minus e to the minus t from 0 to a half, which is minus root 2 e to the negative half minus e to the 0. So depending on how far you want to go with that, looks like we'll have a root 2 times 1 minus e to the, in fact, as long as we're doing that, let's just write that as a 1 over root e, like that. And that looks pretty good. You can go a little further and make this root e minus 1 over root e. If you really want, you can rationalize. This would be e minus root e over e. You can do that, which is root 2 over e, e minus root e. Okay. Now, just like we did with converting that that arc length integral in xy in the rectangular coordinate system. Just like we converted that, we can also convert this guy, the surface area of a surface of revolution. Okay, we'll say this is a to b. And remember, we had that function in there. We call it r of x, and then we had x. We had r of x, and then what was that again? Okay, I need to recall that formula. Let's see. We had 1 plus the, well, if we're going with respect to x, then we would have y prime of x squared inside. And remember, we had the alternate formula, c to d, we'll say. And then you had 1 plus, instead of y prime, we had x prime of y dy inside there. And we had r of y in here. R of y. That was the radius. Okay, as a function of y this time. So we've got 2 separate formulas over here. Again, just a little bit of work manipulating this derivative, and you can easily work it into this formula here. Okay, remember with respect to x, this r of x is revolved about the x-axis, so this is actually y, and that becomes just a g of t, because y is g of t. Okay, and here you have r of y, but with respect to the y, and if you're integrating with respect to y, you're revolving about the x, and this is x here. This is the distance to the y-axis. Well, that's just f of t, so that's why it shows up over here. Okay, so look at it that way. Okay, now the surface area. We'll see, we're going to work this example. Find the area of the surface generated by revolving this curve about the x-axis and then the y-axis. So we don't need to go into okay, so okay, I was saying this is the radius here. All right, let's go ahead and try a problem. It says find the area of the surface generated revolving the curve about the x-axis and then the y-axis. There's 2 problems in one here. Okay, so first of all, let's take a look at what this looks like. X equals t. So you can see really this is just it's just a line. Y equals 4 minus 2x. So 4 slope is minus 2, so it comes through here and here. Okay. So for t between 0 and 2, we really actually only have, whoops, took more out there. This portion to this portion. And it's revolved about, let's do the x-axis first. So coming around this way. Okay, so we have this situation. Remember that right frustrum that we set up. So we're going to have surface area, 2 pi. And now we will have y in here. Square root of y prime squared plus x prime. squared dt, 0 to 2. So it's 2 pi, 0 to 2. Now y is equal to 4 minus 2t. And now we'll put in the derivatives. Whoops. That's a dt. Okay, so derivatives. In here, x prime equals 1, and y prime equals negative 2. So we have a 1 squared plus a negative 2 squared. That's 2 pi. All of that's just the root 5. So we have a root 5 out here. And we have 4 minus 2t dt. Okay, now that equals 2 pi root 5. Let's evaluate here. Got a 4t minus t squared from 0 to 2. So we have 2 pi root 5. And then that's an 8 minus 4. So it looks like that becomes, I'll put it here, 4 is 8 pi root 5. Okay. Now, take us back up here. This time it's going to spin around this way. Okay. So this one, we had this type of shape here. This one is going to look like this. So it's not really the same. It's a different height. It's and a different base. Okay. So it is a difference. In this case, it is a cone. And we're looking at the surface area of that cone. So let's set it up this way. 2 pi. This time we're going to go from 0 to 4 because that's the intersection up here is at 4. And we want x because that's the distance out to that curve. And then you still want the same derivatives in there, which are going to give us a 5. Remember, taking those derivatives. So that part isn't going to change. 2 pi root 5. But we got to put that x in there. Now, x is equal to t. So end up with 2 pi root 5, t squared over 2 from 0 to 4. That's pi root 5 times 4 squared. 0 will cancel. So it's just 16 pi root 5. Looks like it's double the other one. Okay. Now here's one more. We're going about the y-axis now. So let's see what we have here. Now, you might recognize this. Looks like an ellipse. And it looks like it will be centered at the origin. In fact, it's a circle because this number is the same as this one. So it actually looks like it's going to be a sphere. Okay, now you can verify that if you just write it this way. So I got x squared over 25 is cosine squared, and a y squared over 25 is a sine squared. Adding together, you'll get a 1, and then you'll see the x squared over 25, y squared over 25 equals 1. So it's x squared plus y squared equals 25. So you see it's a circle with radius 5. Okay. We're looking for the surface area. Okay, now it might not be an entire circle because this only goes to pi over 2. That means, what it means is that we are going to have this quarter circle at 5. And this one over here is 5, 0. So we're doing a quarter circle now. And it's revolved about the y-axis. So that will generate a hemisphere. It'll be a hemisphere, and we want the surface area. So it's just half full 4 pi r squared. This is the number we're looking for. We should get to this by the time we're done cutting 2. So it's 2 pi r squared. Let's see if we don't get that. So we'll start off 2 pi, 0 to pi over 2. We want the radius, which will be x, which is 5 cosine t. That's what x is. That's the distance in here, which is our r value. R equals x. Then you want the square root. Now the derivatives. We got a minus 5 sine t squared. And the other derivative, that's this one. The other one would be a 5 cosine t quantity squared dt. So that's 10 pi, 0 to pi over 2. Inside here you got 25 sine squared t plus 25 cosine squared. And you can pull that 5 out, so now we got a 15 pi, 0 to pi over 2. And you got sine squared plus a cosine squared is a 1. So this is all we have right here. Okay. Let's see. Okay. So it looks like we have a 15 pi with a t from 0 to pi over 2. So that makes 15 pi times pi over 2, which is 15 pi squared over 2. Okay, so up here we said we thought we would get this. This circle has radius 5, so it would be 2 times pi times 2.5. In fact, let's write that. That 2.5. Let's write that as. I mean, you don't have to, but write it as 5 over 2, and I'll square that. So this ends up as 2 pi times 25 over 4, which is, let's see, 25 pi over 2 pi squared. This is, this should have been a squared here, my original formula. That's for the surface area. It's 4 pi r squared. 4 pi squared r squared. No, it's just 4 pi. Yeah, it's just 4 pi r squared. And then you divide it by 2, so we should have this. Let's see what happened here. Derivatives, 5. 10. Let's see what happened over here. I pulled out that 5. This going to be a 25 here. So pull that 5 out of here, made that. Well, that's 10. That should actually be a 50. Sorry about that. So that was a 50 pi. And here, that should have been, let's see, that's a 50. That's a power 2. Okay. See what's going on there. Okay, so I can see where that's coming from, why that's a 25 now. After that 2 is gone. But I still don't like my pi squared. Okay, something isn't right here. 2. Okay, back again. Okay, I erased a couple things up here. You can see them in the previous few seconds there. Discovered a mistake in here. I don't want to redo all this. So in here, I had lost my cosine when I went. I think I went from this step to this step. But in any case, it's in here, and I pull out the 5 from here. This is all just equal to 25. And I pull out a 5 and make this a 50. My cosine, integral is a sine, evaluated is in here, I get a 50. Okay, now up here, what I was trying to show was this. This is what we should get because it's half of the hemisphere. And this was the formula for a surface area of a sphere. So my radius is 5, so I should have 2 times pi times 5 squared, which is 50 pi. Okay, so they do match, and it makes more sense now. Okay, sorry about that delay there.